Finding a duplicate number inside an array is straightforward if you use a hash set to track what you've seen. But when you are restricted to linear time and strict constant space, those easy data structures are off the table. We have to solve the problem without allocating extra memory. This diagram shows the required perspective shift. Instead of looking at a static list of numbers, we treat the array as a linked list. By lifting the values out of their boxes, we define a clear rule. The specific value inside an index is the exact next index you must jump to. The problem guarantees that all values in our array are between 1 and n. Because there is no zero value, any path leaving index 0 can never point back to the starting line. The duplicate number creates a structural inevitability. When two different nodes hold the exact same value, they must point to the exact same index. This forces the path to merge and traps any subsequent jumps into a closed loop. The duplicate value dictates this convergence. Our array functions exactly like a one-way lasso, and the duplicate number we need to find is the physical knot where the loop begins. To prove this cycle exists, we use phase 1 of Floyd's algorithm. We deploy two moving pointers onto the track, a slow pointer, often called the tortoise, and a fast pointer, the hare. Here in this diagram, we establish their movement. Both start at the beginning of the array. The slow pointer moves exactly 1 step per turn, while the fast pointer moves exactly 2 steps per turn. Once both pointers enter the loop, the fast pointer shrinks the distance between them by exactly 1 step per turn. It will lap the slow pointer, guaranteeing they crash into each other on the exact same node. The collision proves the array has a loop. However, the exact location of the crash site is mathematically arbitrary. They meet somewhere inside the loop, not necessarily at the knot where the duplicate actually hides. Looking at this schematic, we define the exact geometry of the collision using 3 variables. L is the distance from the start line to the knot, x is the distance from the knot to the crash site, and c is the total circumference of the cycle. At the moment of impact, the slow pointer traveled down the initial runway, L, and walked into the loop until it reached the crash site, x. Its total distance is L plus x. The fast pointer traveled that exact same path, L plus x, but because it moves quicker, it completed an unknown number of full cycles, represented by n times c, before the collision. We know the fast pointer travels exactly twice the speed of the slow pointer, meaning it covered exactly twice the total distance. You can pause the video here to set up an algebraic equation and attempt to solve for L. We set the fast distance equal to double the slow distance. 2 times L plus x equals L plus x plus nc. Subtract the single L plus x from both sides, and we isolate L. L equals nc minus x. This equation gives us our exact coordinates. L is the physical distance from the start line to the knot. nc minus x is the remaining distance from the crash site to the knot. The math proves these 2 separate paths are identical in length. In this schematic, we apply the proof to phase 2 of the algorithm. We reset the slow pointer back to the very beginning of the array and leave the fast pointer right where it is at the crash site. Next, we adjust their movement. Both pointers are now set to travel forward at a constant speed of exactly 1 step per turn. Because the distance from the start to the knot perfectly matches the distance from the crash site to the knot, walking forward step by step guarantees both pointers arrive at the entrance simultaneously. This reference sheet summarizes the mechanics. Reading values as pointers creates a lasso. Phase 1 detects the cycle by colliding the slow and fast pointers. Phase 2 leverages L equals nc minus x to locate the duplicate exactly where the cycle begins. By shifting our perspective from static data to a topological track, we calculate the intersection without allocating extra arrays or hash sets. The mathematical properties of the cycle itself isolate the duplicate number.